Hello, welcome back to the playlist of lectures on hypothesis testing. In this lecture, we will focus on the final lecture, namely power of the hypothesis test and evaluation of beta. We have understood in detail about alpha, the type 1 error, its selection and its influences. We haven't dwelled much into the details of the type 2 error beta, how to measure beta, and its influence on the so-called power of the hypothesis test. We will focus on the power of the hypothesis test and its relationship to beta in this final lecture. Let's get into the video. By intuition, a good hypothesis test is a one that minimizes rejecting H0 when it is true, that is minimizing type 1 error, and that maximizes rejecting H0 when it is false, that is maximizing 1 minus type 2 error. In other words, minimizing type 2 error. While the type 1 error alpha, that is the level of significance for the test, is controllable via the methods that are used to conduct the hypothesis test, one can attempt to keep the type 1 error alpha minimum. However, the criteria to maximizing rejecting H0 when it is false requires keeping the type 2 error, that is beta, minimum. Controlling beta is not straightforward, and hence we need to understand what are the factors that influence beta. Where H0, that is mu or pi equals hypothesized value, is tested against HA, that is mu or pi greater than hypothesized value, alpha determines the type 1 error when the true population characteristic mu or pi equals the hypothesized value. Alpha determines the shaded area under the sample statistic distribution curve, extending from the critical value corresponding to alpha towards the increasing values of the sample statistic until where the probability curve meets the sample statistic axis. Where HA, that is mu or pi, is greater than the hypothesized value, a sample statistic x bar or p less than the critical value is not rejected when H0, that is mu or pi equals the hypothesized value, is true. That is a desired result too. Whereas the same sample statistic x bar or p is not rejected even when H0 is false. That is not a desired result. That is in fact a type 2 error. Notice that x bar or p is shown on the distribution where mu or pi is greater than the hypothesized value. This is because of the condition that H0, that is mu or pi, equals hypothesized value is false. In fact, failure to reject H0 even when it is false happens with any value of x bar or p less than the critical value, shown by the shaded area to the left of the critical value on the distribution curve where population characteristic mu or pi is greater than the hypothesized value. Shaded area to the left of the critical value on the distribution where population characteristic mu or pi is greater than the hypothesized value represent the probability that the sample statistic takes a value less than the critical value when H0 is false. This shaded area equals the probability of the type 2 error, which is beta. Estimating beta is not straightforward. Beta is influenced by three factors. 1. True population characteristic mu or pi. 2. Alpha value. And 3. The sample size n. Let's take one factor at a time, keep rest of the two factors constant, vary this factor and study its influence on beta. Let's start with the true population characteristic mu or pi. Influence of true population characteristic mu or pi for given values of alpha and the sample size n on beta. When the difference between the true population characteristic mu or pi and the hypothesized value is small, that is when both are closer to each other, beta is large. That is, when H0 is false, the probability that a sample statistic x bar or p taking a value less than the critical value increases as the true population mean gets closer to the hypothesized value. When the difference between the true population characteristic mu or pi and the hypothesized value is large, beta is small. That is, when H0 is false, the probability that a sample statistic x bar or p taking a value less than the critical value decreases as the true population mean moves further away from the hypothesized value. Therefore, beta is not a constant and it varies with the value of the unknown true population characteristic mu or pi. Larger the deviation, lesser is beta. Lesser the deviation, larger is beta, where deviation is the difference between the hypothesized value and the true population mean. Since the true population mean is unknown, beta can be estimated only after choosing a value from a set of a few selected values of interest for the true population mean. Influence of alpha on beta for given values of mu or pi and sample size n. Since alpha decides the critical value for the sample statistic beyond which H0 is rejected, alpha has a direct influence on beta. When alpha reduces, beta increases. That is, when H0 is false, the probability that a sample statistic x bar or p taking a value less than the critical value increases as alpha reduces. On the contrary, when alpha increases, beta reduces. That is, when H0 is false, the probability that a sample statistic x bar or p taking a value less than the critical value decreases as alpha increases. Therefore, beta for given values of population characteristic mu or pi and sample size n increases as alpha is decreased and decreases as alpha is increased. Influence of sample size n on beta for given values of population characteristic mu or pi and alpha. Increasing the sample size n results in narrowing of the sample statistic distributions, which results in the tails of the distributions getting pulled towards their respective centers. Therefore, the shaded area to the left of the critical value beta reduces. Beta reduces with increase in sample size n. Decreasing the sample size n results in widening of the sample statistic distributions, which results in the tails of the distributions getting pulled away with respect to their centers. Therefore, the shaded area to the left of the critical value beta increases. Beta increases with decrease in the sample size n. In summary, probability of the type 2 error, that is beta, is influenced by three factors: true population characteristic mu or pi, alpha value, and the sample size n. Reduces with increase in difference between the hypothesized value and the true population characteristic mu or pi, and increases with the reduction in the above difference. Reduces as alpha increases and increases as alpha reduces. Reduces as sample size increases and increases as sample size reduces. Each of the above three cases are stated, while the other two factors are assumed unchanged. Therefore, with the true population characteristic being unknown, the probability of the type 2 error, that is beta, is reduced by carefully choosing the value of alpha. We discussed about this already. Additionally, a possible increase in the sample size can help reduce beta. By definition, the power of a hypothesis test is the probability of rejecting the null hypothesis. We already know type 1 error alpha determines the probability of rejecting the null hypothesis when H0 is true. What still remains to be determined is the probability of rejecting the null hypothesis when H0 is false. Power of a hypothesis test when H0 is false equals probability of rejecting H0 when H0 is false. That equals 1 minus probability of not rejecting H0 when H0 is false. Probability of not rejecting H0 when H0 is false equals beta. Therefore, power of the hypothesis test when H0 is false equals 1 minus beta. Power of a hypothesis test when H0 is false equals 1 minus beta. 1 minus beta is the area to the right of beta under the sample statistic distribution curve for the true population characteristic which is greater than hypothesized value. Note, though the illustrations for beta all along has been with an example situation wherein the true population characteristic is greater than hypothesized value, the same concepts can as well be established using cases where the true population characteristic is less than the hypothesized value as well. Based on the influence of three different factors on beta, and since the power of the test when H0 is false equals 1 minus beta, we can state that the power of the test when H0 is false increases as the difference between the true and the hypothesized value increases as alpha increases, and increases as the sample size increases. Let's apply the learning so far and estimate beta and the power of the test with an example. A cigarette manufacturer of a particular brand claims that the mean nicotine content in their cigarettes is 1.5 milligrams. We may investigate this claim by testing H0, that is mu equals 1.5 versus HA, that is mu is greater than 1.5. The claim of the manufacturer implies that the nicotine content at max equals 1.5 milligrams, may be less but certainly not more. Therefore, we have chosen the alternative hypothesis HA that challenges this claim, contests to reject H0 if a strong evidence is available that the nicotine content is more than 1.5 milligrams. Let's choose a level of significance alpha for this test as 0.01. A random sample of 36 cigarettes are chosen for this test. And let's consider that the standard deviation of the population, sigma, is known and is 0.2 milligrams. The aim of this test is to determine beta and the power of the test for a selected value of true population mean. With mu equals 1.5, the alternative hypothesis being HA, that is mu, is greater than 1.5, and the level of significance alpha equals 0.01, we have a situation as illustrated here. Let's proceed to calculate the critical value Z star on the standardized normal distribution, that is the Z curve, above which the null hypothesis will be rejected. Critical value Z star can be derived from the Z table given the value of alpha that equals 0.01. Alpha equals 1 minus probability of Z taking a value less than Z star. Therefore, probability of Z taking a value less than Z star equals 1 minus alpha. Probability of Z taking a value less than Z star equals 1 minus 0.01, which is the value of alpha, which in turn equals 0.99. Probability of Z taking a value less than Z star equals 0.99 when Z star equals 2.33 as per the Z table. Therefore, critical value Z star equals 2.33. We also know Z star equals x bar star minus mu divided by sigma divided by square root of n, where x bar star equals the critical value of the sample mean above which H0 will be rejected, mu equals the hypothesized mean, which is 1.5, sigma equals the population standard deviation for nicotine, which equals 0.2, and n equals the sample size, which is 36. Substituting 2.33 for Z star, we can arrive at x bar star as in 2.33 equals x bar star minus mu divided by sigma divided by square root of n. X bar star therefore equals 2.33 multiplied by sigma divided by square root of n plus mu. Substituting the values for sigma, mu and n, we have x bar star equals 2.33 multiplied by 0.2 divided by square root of 36 plus 1.5. X bar star therefore equals 1.578. We will reject H0 for any sample mean X bar that is greater than 1.578 and fail to reject H0 for any sample mean X bar that is less than 1.578. As said earlier, the aim of this test is to determine beta and thus the power of the test for a chosen value of a true population mean. Suppose we chose a value of 1.6 milligrams as the true population mean. We have the situation as shown besides. Beta equals the area under the curve to the left of X bar star, which equals 1.578 when the true population mean equals 1.6. We determine the shaded area for beta under the standard normal Z curve. Zt, value corresponding to X bar star on the standard normal Z curve, equals X bar star minus mu divided by sigma divided by square root of n, where X bar star equals 1.578, mu is the selected true population mean, that is 1.6, sigma is the population standard deviation, that is 0.2, and n equals the sample size, that is 36. Substituting the values we have, Zt equals 1.578 minus 1.6 divided by 0.2 divided by square root of 36. Zt therefore equals minus 0.66. Beta equals probability of Z taking a value less than Zt, which equals probability of Z taking a value less than minus 0.66. From Z table we get probability of Z taking a value less than minus 0.66 equals 0.2546. Therefore, beta equals 0.2546, that is 25.46%. Which means the probability of committing the type 2 error equals 0.2546. 25.46% of times we will fail to reject H0 even when H0 is false, when the test is repeated over many samples over a long period of time. Power of the test when H0 is false equals 1 minus beta, which equals 1 minus 0.2546. Power of the test when H0 is false thus equals 0.7454, that is 74.54%. When the test is repeated over a large number of times with different random samples, the test will successfully reject H0 74.54% of the times when H0 is false. That brings us to the end of the example where the null and the alternative hypothesis were H0, that is mu equals 1.5, and HA, that is mu is greater than 1.5. Level of significance alpha for this test was 0.01. Standard deviation of the population sigma was 0.2 mg, and sample of 36 cigarettes were considered. We estimated probability of the type 2 error beta as 0.2546 and power of the test as 0.7454. The test would successfully reject H0 74.54% of times when H0 is false for selected true population mean of 1.6 mg. That brings us to the end of the last lecture in the playlist for hypothesis testing, wherein we understood the factors that influence beta and estimating beta and the power of the test when H0 is false. That winds up our discussion on the topic of hypothesis testing. See you soon with the next playlist on essential statistics for data science. Bye until then.